Question B. Find the dual LP for each of the problem. We can see from the question the original problem is the maximum model, so the dual is the minimum model. In primal, number of variables is 4, which is x1, x2, x3, and x4. So, for the dual, number of constraints is 4. In primal, number of constraints is 2. So for the dual, number of variables is 2, which is y1 and y2. Right hand side of constraint in primal is equal to coefficient of the objective function. Coefficient of first variable in primal, which is 2 and f, is same as coefficient of the first constraint of the world. The sign of each constraint of the world is based on sign restriction of primal, which we can see it is larger or equal to. The sign restriction of the dual, which is URS, is referred to the sign of each constraint in primal, which is we can see equal to 300. Question C. Find the dual solution for each of the LP based on their optimal tableau. We have to convert all the sign of constraint to an equilibrium constraint, so we subtracting the axis variable minus E for all the constraints, like this, and this. Okay. An artificial variable must be added to each constraint because all the constraints do have a basic variable. So we add plus A to all the constraints like this. We must add minus M as the coefficient of the artificial variable in row 0 because this is the minimum problem. Like this. Okay. And the objective function must equal to 0. And don't forget to enter all the variables to the sign restriction. Then we transfer the coefficient of all the variables into the initial table, like this. We need to eliminate A1, A2, A3, and A4 from the row 0 by simply replace the row 0. Like this. How? We look at the first column A1. In row 1, we can see have coefficient 1 and the sign is positive, so we minus M row 1. Then we look at column A2. Row 2 have coefficient 1. The sign is positive, so we minus MR2. Then same as column A3. Row 3 have coefficient 1. The sign is positive, so we minus MR3. For column A4, Row 4 have coefficient 1, the sign is positive, so we minus MR4. Then we get this. Now we get the new coefficient for each variable in row 0. We just key in the coefficient in the updated table. Basic variable is not changed yet and the update value not optimal yet because all the coefficient in row 0 is non-negative. So we need to find the entering variable. We need to choose the most positive coefficient in row 0 because this is the minimum problem. So the most positive is y2, so we can conclude that y2 is the entering variable, which is the new basic variable. Next, we need to find the leaving variable by using ratio method, which is we need to divide the right hand side with this column, which is entering variable. Then we get this ratio. The row with the smallest ratio will be the leaving variable. As we can see, row 1 has the smallest ratio and this will be the leaving variable. Okay. N is the private number, so we need to change it to 1 by divide by n. So we can like this. The other row in column y2 must have 0 coefficient and the ERO for other row need to refer to R1. Okay. So we calculate all the coefficient. Table 1 is not optimal yet because they still have a positive coefficient in row 0. So we continue. Find the entering and leaving variable. Then we continue with table 2 and table 3 with the same step as we find entering and leaving variable, and the last table is table 4, which is when all the coefficient, the variable in row 0 is non-positive coefficient, hence optimal solution is arrived. Its value of variable is y1 equal to 5/9, y2 equal to 7/9, and the minimum W is 400.
Okay, Assalamualaikum. Today I want to share how to solve the problem by BM method manually. Okay, first we have the maximum problem and we have two constraints. Okay, first thing first, we must to convert this LP model to the standard form like this. How? We can see that the boost of this constraint doesn't have the basic variable. So we must add the artificial variable as the basic variable. For the first constraint, we add A1 and the second constraint, we add A2. Okay, so at the objective function, we must add a positive m as the coefficient for the artificial variable. And why positive m? Because this is the maximum problem. Okay, and the objective function must equal to 0. Okay, like this. And one more thing, for the right hand side, for the constraint must non-negative. Okay, this is the complete standard form, and we must to transform it to the initial tableau like this. Okay, this is the for the row 0, which is the objective function, and this is the row 1 as the first constraint, and this is row 2, the row 2 as the second constraint. And don't forget to write down the basic variable and the non-basic variable. The next step is we need to eliminate the artificial variable at the row 0. Okay, this is row 0. The artificial variable is A1 and A2. Okay, why we need to eliminate? Because we want to create the new row 0. Okay, how? We must generate the ERO for the row 0. Okay, first look at the column A1. Look at the row 1. Row 1 have a coefficient 1. The sign is positive, so we must do minus MR1. And look at the row 2, the column 2, sorry. And we can see that the row 2 have coefficient 1 and the sign is positive, so we must minus MR2. Now we get the new coefficient for each variable in the row 0, and don't forget to calculate the new right hand side for the row 0. And now we just key in all the coefficient in the updated tableau, and we get like this. And the basic variable is not changed. Okay, and write down the basic variable and non-basic variable at the bottom of the updated tableau. Okay, this updated tableau is not optimal yet because all the coefficient for each variable in row 0 is negative. So we must find the entering variable. How? We need to choose the most negative coefficient in row 0. So we can see this is the most negative. Okay, so we can conclude that x1 is the entering variable. The entering variable will be the basic variable. Okay, first select this column. Okay, now we need to find the leaving variable by the ratio method. Okay, the ratio method is where we need to divide the right hand side with this column. Okay, we get this is the ratio. For row 1, we didn't need to find, for the row 0, sorry, we didn't need to find the ratio, and we just find the ratio for the constraint only. And we can compare this ratio. We choose the smallest ratio. Okay, and we get the A2 is the smallest ratio. Select this row. Okay, this is the pivot number where we need to change it to be the 1. and we must to multiply with the reciprocal, and we get the new row 2 is this. And this is the ERO for the row 1, where we need to refer to row 2, and negative 2 is come from here. Okay, the sign is negative because at the row at the column this is the sign is positive, so we get the new row 1. The same way for the row 0, this is the ERO for the row 0, and we get the new row 0. The table 1 is not optimal yet, so we need to find the entering variable. So we can see that this is the most negative coefficient. So x3 is the entering variable. Okay, select this column. Okay, find the ratio. So the ratio is, the smallest ratio is at the row 1. Okay, select this row, and this is the pivot number. So what the ERO? The ERO is the time by the reciprocal for this pivot number. So we will get the new row 1 is like this. Okay, for row 2, we need to find the new row 2 by this ERO, and we just refer to the row 1, and the new row 2 is this. Okay, for ERO, the ERO for row 0 is this, and the new row 0 is this. Okay, we can see that the basic variable is changed to x3 and x1. W2 is not optimal because the coefficient for x4 is -2 at the row 0. So we conclude that x4 is the entering variable. So select this column and find the ratio. Okay, the smallest ratio is at row 2. So this as x1 is the living variable. Okay, select the row 2. Now, this is the pivot number. We need to find the ERO. By the ERO, we can find the new row 2. Okay, the ERO for the row 1 is this, and we can find the new row 1. Then the last is the ERO for row 0, and the new row 0 is this. Okay, we can see that the all coefficient at the row 0 is positive. So we can conclude that table 3 is the optimal table, with the basic variable is the x3 and x4. Some estimation for the table 3. Okay, look at the coefficient. All the coefficient in the row 0 is non-negative, so this is the optimal table. And all the basic variable, which is the x3 and x4, is 0 coefficient in row 0. So, and one more thing, the non-basic variable has non-zero coefficient in row 0. So this is the unique solution, unique optimal solution, where the value of x1 and x2 is 0, x3 and x4 is equal to 50, and z is 400. We can look at the right hand side.
Assalamualaikum and hello everyone. Today I want to show you how to use the Big M method calculator. First of all, we need to insert the total variable and constraint that given on the question. Next, we need to insert all of the information given from the question and then click find. The output will be shown here. As you can see, A1 is in the row 1, A2 is in the row 2, the column of XP is the right hand side, and the last row is row 0. This is the LP model that we have inserted earlier, while this is the standard form, which contain artificial variable. Therefore, penalty rule need to be applied in this problem. This is the initial tableau. As you can see, there is a coefficient in basic variable on row 0. Thus, this row 0 need to be replaced. This is the new row 0. This tableau is not optimal yet because in maximum problem, the coefficient in row 0 must be non-negative. Therefore, we need to find the entering and the leaving variable. This green arrow indicates the entering variable and this red arrow is for the leaving variable. And 8 need to be 1 in this column and the other need to be 0 so that x1 will be the basic variable in the next tableau. This is the ERO to get this tableau. This tableau is not optimal yet because there is a negative coefficient in row 0. This is the entering variable and this is the leaving variable. And the pivot element is 15/4. This is the ERO to get this tableau. As you can see, there is a negative coefficient in row 0. Thus, this tableau is not optimal yet. This is the entering variable. And this is the leaving variable. This is the ERO to get this tableau. As you can see, this tableau is optimal because there is a non-negative coefficient in row 0. Hence, the optimal solution is arrived with the value of variable as x1 equal to 0, x2 equal to 0, x3 equal to 50, x4 equal to 50, and z equal to 400.
First, you have to change the primary objective function and constraint to the dual objective function and constraint. The application that we use to solve this problem is LPSolve IDE 5.5.2.5. The objective function is minimum z equal to 300x1 plus 300x2. The first constraint is 2x1 plus 8x2 greater than equal to 4. The second constraint is 3x1 plus x2 greater than equal to 2. The third constraint is 4x1 plus x2 greater than equal to 3. The fourth constraint is 2x1 plus 5x2 greater than equal to 5. Click Action and then click Solve. For the result, the value for S1 is 5/9, S2 is 7/9 and the Z value is 400.